Okay, let's dive into something today that really messes with how we usually picture things.
You mean the whole particle versus wave idea?
Exactly. We tend to think, okay, things are either waves, like light waves, maybe sound waves, or they're particles, little objects like a baseball or even an electron.
Right, neat little boxes. Light's a wave, and electron's a particle. End of story.
But, well, what if the universe is actually a bit more subtle, maybe even a bit mind-bending?
That's precisely where we're headed, this core idea in physics called wave-particle duality.
Duality.
Meaning both.
Exactly. It means that both matter, like electrons, and radiation, like light, can show properties of both waves and particles, depending on how you look at them.
Huh, that sounds weird, but you're saying there's evidence.
Oh, absolutely. Solid experimental evidence. And it's not just theory. It leads to some incredibly powerful technologies we use every day.
Okay, so that's our mission for this deep dive then. Let's unpack this duality.
We'll look at the evidence showing particles, specifically electrons, acting like waves, which still sounds strange to say.
It does take some getting used to.
And then we'll switch gears a bit to X-rays. How are they made? What are they like? How do we use them? And crucially, how does this all tie back to that wave idea?
And the goal is really to give you a clear sense of this fascinating concept and why it actually matters beyond a physics classroom.
Right. So where do we start? Maybe with light.
That's a good starting point. For a long time, light seemed straightforwardly like a wave.
Yeah, I remember learning about things like interference patterns, diffraction, light bending around corners, classic wave behavior.
Definitely wave phenomena. But then experiments started cropping up that didn't quite fit. The photoelectric effect, for example.
That's when light hits metal and knocks electrons off?
That's one. Explaining that purely with waves was, well, problematic. And the quantum effect, how light scatters off particles. It really behaved as if light itself was made of little packets of energy. Particles.
We call those photons, right?
Exactly, photons. So suddenly, light was acting like both a wave and a particle. A real paradox.
Okay, so light's weird. It can be both.
And that set the stage for Louis de Broglie in 1924. He had this really bold thought.
Which was?
Well, he thought if light, which we always considered a wave, can act like a particle, maybe particles like electrons could act like waves. Sort of a symmetry argument.
Oh, okay. That's a leap. Did he have math for that or just an idea?
Oh, he had math. He proposed a specific relationship. The wavelength of a part, let's call it lambda, is related to its momentum.
P-man. Mass times velocity.
Right. And the link is Planck's constant h. So h actually hp. The wavelength is Planck's constant divided by the momentum.
Okay, hold on. H will hp. If p is momentum, does that mean everything has a wavelength, like this microphone, my chair, a baseball?
According to de Broglie, yes. Everything with momentum has a wavelength.
But I've never seen a baseball act like a wave. It doesn't diffract around the batter or anything.
And you never will. That's where the scale comes in. Planck's constant hh is incredibly, incredibly tiny.
Right, like 10 to the minus 34 or something crazy.
Exactly. So for something with the mass and speed of a baseball, its momentum p is relatively huge. You divide that tiny h by a big P, and the resulting wavelength is, well, it's astronomically small.
Smaller than an atom.
Oh, vastly smaller. Billions of times smaller than even the nucleus of an atom. It's so small that any wave effects are completely impossible to detect for everyday objects.
Okay, so the math works, but it's just irrelevant for big stuff.
Pretty much. But now, think about an electron.
Tiny mass. Really tiny.
Extremely tiny mass. So even if it's moving quite fast, its momentum p is still very, very small compared to a baseball.
So h divided by a small p gives a bigger all.
A much bigger all. Not huge, but potentially big enough to be significant. If you calculate the de Broglie wavelength for an electron accelerated through a decent voltage, you get a wavelength maybe around the size of an atom, or the spacing between atoms in a crystal.
And if the wavelength is similar to the size of the things it interacts with?
Then you might actually see wave behavior, like diffraction.
So did anyone actually see it? Was there proof?
There was, and it came surprisingly quickly, actually, in 1927.
Just a few years after de Broglie's idea.
Yep. 2 separate experiments, basically simultaneously. Davison and Germer in the U.S., and G.P. Thomson in the U.K.
G.P. Thomson. Wasn't his father, J.J. Thomson, the one who discovered the electron as a particle?
The very same. Kind of ironic, isn't it? The father proves it's a particle, the son proves it's a wave. Physics is fun like that.
Huh. So what did they do? How did they show electrons were waves?
Davison and Germer fired a beam of electrons at a nickel crystal. Now, if electrons were just tiny particles, you'd expect them to just scatter sort of randomly off the surface atoms.
Like little balls bouncing off bumps.
Right. But that's not what they saw. They found that the electrons scattered much more strongly in very specific directions. It formed a pattern.
A pattern.
Like a diffraction pattern. The same kind of pattern you get when waves, like light waves or even X-rays, pass through a regularly spaced structure, like the atoms in a crystal.
Whoa. So the crystal lattice was acting like a diffraction grating for the electron waves.
Precisely. G.P. Thomson did similar experiments, firing electrons through thin metal foils, and he saw diffraction rings on a detector screen. Again, classic wave behavior.
That's incredible. Direct proof.
Undeniable proof. It confirmed Broglie's hypothesis, and it really cemented this wave-particle duality idea for matter. It was revolutionary. Thomson actually shared a Nobel Prize for demonstrating the wave nature of electrons.
So electrons are waves, sometimes.
Or they have wave properties that manifest under the right conditions. And this wasn't just, a neat physics trick. It immediately suggested something very practical.
Which leads us to the electron microscope.
Exactly. A truly transformative technology based directly on the wave nature of electrons.
Why is it so much better than a regular light-based microscope? What's the advantage?
It all comes down to resolution, the ability to distinguish fine details.
How close two things can be before they just blur into one.
Right. And the fundamental limit on resolution for any microscope is set by the wavelength of whatever you're using to see the sample.
Okay.
So optical microscopes use visible light. The wavelengths of visible light are roughly 400 to 700 nanometers. That physical wavelength puts a hard limit on how small a detail you can clearly see.
Can't see things smaller than the wave you're using to look at them?
Pretty much, yeah. It limits optical microscopes to maybe 1,000, 1,500 times magnification, effectively, and a resolution around 200 nanometers.
Still pretty good, but limited.
Limited if you want to see really small stuff.
Okay.
Now, electron microscopes use a beam of electrons instead of light.
And we just established that electrons have a wavelength equals hp.
Exactly. And you can control the momentum, p, by accelerating the electrons through a voltage. If you accelerate them to high speeds, you give them significant momentum.
Which makes their de Broglie wavelength really, really small.
Much, much smaller than visible light. We're talking fractions of a nanometer.
Ah, so a vastly smaller wavelength.
Means vastly better potential resolution. Electron microscopes can resolve details down to the scale of atoms and achieve magnifications of, hundreds of thousands of times, even millions.
So we can see viruses, molecules, the insides of cells in incredible detail.
All thanks to harnessing the wave nature of the electron. Of course, they're more complex. They use magnetic fields as lenses instead of glass and need a vacuum because electrons scatter off air molecules easily. But the core principle is that shorter wavelength equals higher resolution.
Amazing. And you mentioned earlier that the electron diffraction patterns look like X-ray diffraction patterns.
I did. That provides a really nice link to the other part of our discussion today, X-rays.
Right. So what are X-rays? We hear about them all the time, especially for medical stuff.
They are another form of electromagnetic radiation, just like visible light, radio waves, gamma rays. They're all part of the same spectrum.
But different energy, different wavelength.
Exactly. X-rays sit in the high-energy part of the spectrum. That means they have very short wavelengths and high frequencies compared to visible light.
And how do we make them? Is it like a special light bulb?
Sort of, but the mechanism is quite different. Usually they're made in something called an X-ray tube, which is basically a vacuum tube.
Okay.
Inside, you have a heated filament, the cathode, which boils off electrons. These electrons are then accelerated across a very high voltage, thousands of volts, towards a metal target, the anode, often made of something like tungsten or molybdenum.
So you slam high-speed electrons into a piece of metal.
That's the basic idea, yes.
Yeah.
When these very energetic electrons hit the target, they decelerate rapidly or knock other electrons around in the target atoms. That interaction converts the kinetic energy of the incoming electrons into electromagnetic radiation, specifically X-rays.
Huh. So it's kind of the opposite of the photoelectric effect. Electrons go in, photons, X-ray photons come out.
That's a pretty good way to think about the energy conversion, yeah. The energy of the X-rays produced depends on the energy of the electrons hitting the target.
Which depends on the voltage accelerating them.
Precisely. Higher voltage means faster, more energetic electrons hitting the target. That allows for the production of higher energy X-rays.
And higher energy means shorter wavelength.
Shorter wavelength, higher frequency. These are often called hard X-rays, and they're more penetrating. Lower voltage gives softer, less penetrating X-rays.
Okay, so we can tune the X-rays by changing the voltage. What are their key properties then? besides being invisible electromagnetic waves?
Well, their most defining property, especially for applications, is their high penetrating power. They can pass through materials that block visible light.
Like soft tissue in the body.
Exactly. But they don't penetrate everything equally. Denser materials, or materials with heavier atoms, absorb them more strongly. That's crucial.
Like bones absorbing more than tissue.
That's the principle behind medical X-ray images. They also travel at the speed of light, naturally. Importantly, unlike the electrons used to create them, X-rays themselves are uncharged, so they aren't deflected by electric or magnetic fields.
And like other waves, do they diffract?
They do. Because their wavelengths are very short, comparable to the spacing between atoms in crystals, they diffract when they pass through crystalline materials. That's a really important property.
Wow.
They affect photographic film. That's how traditional X-ray images were recorded. They can cause materials to fluoresce, to glow, and they carry enough energy to ionize gases, meaning they can knock electrons off gas atoms.
Okay. So high energy, very penetrating, short wavelength waves. And that penetration is key for uses, right?
Absolutely. The most common use is medical imaging, as we mentioned. The differential absorption bone absorbing more than flesh creates a shadow image on a detector or film.
Letting us see broken bones or sometimes other issues.
Right. You can also use contrast agents like barium sulfate, which absorbs X-rays really well, to image soft tissue structures like the digestive tract. And sometimes very high-energy X-rays are used in radiation therapy to target cancer cells.
So medicine is a huge area.
Yeah.
What else?
Well, in industry, they're used for non-destructive testing. You can X-ray weld seams or metal castings or engine parts to look for internal cracks or flaws without having to cut them open.
Like a medical checkup for machines?
Kind of, yeah. And, of course, security screening at airports. Those scanners use X-rays to look inside luggage.
Can't imagine air travel without them now.
And scientifically, that diffraction property we mentioned is huge. X-ray diffraction is a standard technique in materials science and chemistry and biology to figure out the precise arrangement of atoms in crystals.
That's how they figured out the structure of DNA, wasn't it? With X-ray diffraction.
It was a key piece of evidence, yes. Rosalind Franklin's X-ray diffraction images were critical. Astronomers also use X-ray telescopes to study super high-energy objects and events in space, like black holes and supernovae.
Wow, okay, so they're incredibly versatile, from checking bones to checking galaxies.
Pretty much, their unique properties make them invaluable tools.
So let's try and tie this all together. We started with electrons, things we thought were just particles showing clear wave behavior like diffraction.
Right, confirmed by experiments leading to things like the electron microscope.
And then we looked at X-rays, high-energy electromagnetic radiation, definitely waves, but whose interactions and production also involve particle-like energy transfers. And their wave nature, diffraction, is key to understanding material structure.
It all points back to this fundamental concept,
Yeah.
wave-particle duality. It's not just a weird quirk. It seems to be how things are at the quantum level.
The bedrock of quantum mechanics, really.
Absolutely. It was one of those foundational ideas emerging from trying to explain experiments that just didn't make sense with classical physics, black-body radiation, the photoelectric effect, and the electron diffraction we discussed.
So why should you, listening right now, care about electrons being waves or the properties of X-rays? Is it just interesting physics?
Well, it is interesting physics, I think. But it's much more than that. Understanding this duality isn't just academic. It's literally the scientific basis for technologies that shape almost every aspect of modern life.
You mean the X-ray machines, the electron microscopes?
Exactly. Seeing inside the human body, ensuring welds are safe, checking luggage, designing new materials, understanding biological molecules. All of these capabilities rely directly on understanding and applying the quantum behavior of waves and particles.
They're not just abstract ideas. They have incredibly tangible, real-world impacts.
Precisely.
So we've taken this deep dive into, well, the weirdness of the quantum world, seeing how particles like electrons can ripple like waves.
And how waves like X-rays have properties that make them powerful tools, stemming from both their wave nature and their high energy.
It really does make you stop and think, doesn't it?
Yeah.
About what reality is actually like on those tiny scales. It defies our everyday intuition.
It absolutely does. And it leaves us with a really profound question, I think.
Which is,
If everything matter, energy fundamentally exhibits this dual wave particle nature. What does that really mean? Are things ultimately waves or particles?
Yeah.
Or is it something else entirely, something that maybe our classical language just isn't equipped to describe properly?
A fascinating thought to leave you with. As you go about your day, maybe you'll see waves or particles in places you never quite expected.